Good afternoon, everybody. So, another installment of Bayes. I did rewrite notes. As I said, what we're going to do, I think we'll start this Friday scanning and putting them up for you so that you'll have your own copies of these. So, exact same notes, just cleaner without the scribbles. I think it's valuable to watch it being written and then having one that's written yourself. So we'll keep with this. I kind of like it. So I made that a little bit clearer. So we went through the likelihood function for our beta-binomial example. We'll be sticking with that example today, and then we'll switch gears. We'll do a normal example. This is easy. We'll move into binary inference on the mean and the variance in the normal example. There are a lot of things, even though the calculations are relatively straightforward, that are worth discussing in those examples. So in class, we're talking about a lot of concepts. We're putting them together. So even though the calculation isn't too difficult, I'll show you how to do the algebra quickly. I'll show you how I do it, so you can save time, give it a test or something. But also, we're conveying lots of general concepts when we're looking at the priors. We're looking at the posterior, and we're thinking about a lot of different things. So think about it that way in class. Through these examples, they're not just a calculation, there's concepts that we're conveying. Later on, we'll anchor down the mathematics in those concepts. But I do think statistics is just a bunch of concepts. I want something, I want it to be like this, I want it to behave like this, and everything else is just And so in statistics, we choose criteria. And so we choose what to think about when we report. Is it the right thing and does it tell the right story? So I tend to think we're 2/3 qualitative. Good statisticians have very good qualitative skills to know what is important, why they're doing something, and then all the rest of it is the math and computation. My percentages I made up, so it's just a conveyor. So I don't know if it's 2/3 on the base. Okay. We wrote down the likelihood function. We could have done this using the binomial representation. This is just the product of the individual Bernoulli sampling functions that I plugged in there. But instead I thought the xi's are fixed, so I'm plugging in actual data as I go from one end. So that part is fixed, and that's what my notation conveys. Right there, that it's given. Not everybody uses that same notation. So we're inconsistent, sometimes notation-wise, but we're talking about the same thing. Likelihood function is a function of. And I could have written down the binomial expression that looks like that, but it has a constant in front, and choose some of the xi's to account for all the reorders and everything. You would come up with this exact same likelihood function. Again, we're plugging in some of the xi's. That's all that actually matters in the calculation. How many successes did you see? If you throw away all the actual xi's and you just fed some of the xi's, likelihood function is exactly the same. And so that's where the important information is. Right here, number of successes and the number of failures. You also need to know what n is. So usually we're talking about problems where you get to that. Sometimes you have to estimate that as well. It's kind of fun. Prior distributions. So far, we're only talking about conjugate priors, or at least giving you a definition for it. It's a very good starting point because it makes calculations easy. But also, it turns out that a lot of these conjugate priors, the limits of them, limits of the hyperparameters, the parameters that underlie the prior distribution, a lot of the objective priors. I've got to tell you what the objective criterions are so that you understand. It sounds really good, objective, sweet. In what sense? You know, and is that a good sense? Is that what we always want to do? We're talking about that. And a lot of the reference priors, you might say that's a specific type of prior. Objective prior, Japanese priors, or another type, and sometimes those priors are the same priors. In 1D, it turns out they are. In multi-D, nope. So probably not. We're going to be talking about all that. But a lot of these objective priors are limits of conjugate priors. And that's cool. So conjugate priors have the nice thing that the prior and the posterior live in the same parametric family. And the only thing that changes are the parameters in that distribution. For our beta example, our binomial example, beta-binomial, our likelihood function is that, and the conjugate prior is this. So I'll just write down that this is the conjugate prior. Why do we like the conjugate prior? Right now, we've been told that it might be good and it's easy to use.
Just have a question out of curiosity. How common is for priors and posteriors not to be the same family of functions?
Not to be what?
Not to be conjugate priors, not to be the type of function changes when it passes from prior to posterior.
Most default analyses are products of conjugate priors. Sometimes people want to get very specific joint relationships that they impose on something. So if you wanted to encode joint relationships in physics, maybe you could do that using conjugate priors, but a lot of times you'll get different priors out of that. So in multidimensional Jeffreys priors, those need not be conjugated as well. So in a higher dimensional reference case, they're oftentimes not. So I'll tell you more about that. I usually like to do a sensitivity analysis along with everything else to see how much it matters. So at the end of the day, when I go to write a paper, if it's an applied paper, and I'm actually not talking about building a theoretical prior or sampling scheme, instead I'm doing an analysis, I usually pick a couple different priors that all make sense from different vantage points and show it really doesn't perturb the analysis too much, what the impact is. So I like to do that. Usually I'll start with products of conjugates. I usually use their reference form. In multidimensional cases, I might be able to get something that's slightly better. My coverage rates could be improved, but sometimes it's not worth the computational burden. And often I'll try to demonstrate that as well. So at the end of the day, you gotta be able to do a bunch of different things and show whether or not it matters. And if it doesn't matter, that's great. If it does matter, you have to explain it. So what percentage of analyses are conjugate priors? Or products of conjugate priors for each parameter? So marginal conjugacy. Don't know the number, but I'm going to consult everything I've ever witnessed in my brain real quick. A lot, 90% probably. And so it's probably a very good Bayesian that's doing something really interesting with the priors. They want to try out this new prior, show that it actually works well, but you might think of things like Gaussian processes or Dirichlet processes, those sort of process priors. Those are not conjugate, really. They do have some sort of conditional conjugate form, though. We're doing the calculations, or easy, at least conditional. Big answers to that question. I think that's what this class is really entirely about. So I think we're just going to study priors, Bayesian calculations, and study the computation that most people use, like MCMC or something like that. So I think that's the next 3 months, is learning all about that. But most of the time people do fairly rudimentary stuff, is what I see. You don't have to be this brilliant statistician to do a reasonable analysis. And so a lot of stuff just looks like a regression. And if you did it the Bayesian way, it might be good. If you did it the non-Bayesian way, probably pretty similar analysis in that case. We'll see cases in this class where you put a lot of noise into everything, and then being the Bayesian might help you. So in ideal cases, it doesn't really matter if you look at it. Okay, I'm regular. So conjugate prior and our posterior turned out to be this right here. So when I multiply these two things together, the exponent's added effectively, and that's what happened. So Bayes is likelihood times prior. So multiply those two density functions together, and I have the posterior density. You can think about this in a lot of different ways. This prior is a penalty on everything. And so it's hard to think about that formula right there, p to the sum of the xi's plus alpha minus 1 times 1 minus p. n minus some of the xi's plus beta minus 1. But we will notice that the alpha is sitting right next to some of the xi's. So it's kind of acting like a data point in some sense. So how much weight do we want to put there? Do we want to put any? We do have a choice to make it 0. Could do that. No weight, no added weight. Could make it 10,000. And the sum of the xi's right next to the alpha, if they get added in, won't have much influence. So we have some insight that we don't want those parameters to be too large. We want to think about what the parameters actually mean. I like to think about everything in terms of the posterior. How much impact did it have on the posterior in terms of quantities that I want to analyze, maybe the expectation and variance, because that's what everybody else looks at. They're quick summary statistics. If things are normal, you just construct everything. If there's any skewness or anything like that, expectation and variance don't really summarize the distribution at that level. But it's something that at least we're trained to think about right now. And so I might want to think about what is the expectation and what is this variance. So does anybody know what this is? So here's the distribution. It's a beta with these parameters. I've given it a nickname, these parameters right here. I've called these on the left alpha tilde, and these beta tilde. That's just some notation I felt like using to simplify everything. Before, when we talked about the prior, I had a beta distribution right here that goes back one page. I haven't written it down anywhere. Let me just give you some notation for this real quick. This whole quantity right here, this is a beta distribution, density, whatever you want to talk about here. Doesn't matter. One's the area under the curve and one is the curve. And so you tell me one, I can figure out the other. So this is a beta distribution. This function describes it. This is the density form right here. But this is a beta alpha beta. So that's what we call it. There's an extra beta always sitting in there, so when you're talking to people, lots of betas show up. Clarify. We've got beta functions, we've got the beta kernel, and we've got the beta distribution, beta density. And it's underlined by parameters alpha and beta. Oops. So probably should have picked different parameters for that, but every text I ever see has those two parameters in right there. A and B, maybe, you might say. But this is the form. It's when alpha shows up there and beta shows up there. And this normalizing constant is just the inverse integral of the density function. It's the thing that makes it integrate to 1. So it normalizes everything. It doesn't have any keys in there. So the posterior distribution is this. And I've said it's updated the parameters to be alpha tilde and beta tilde. Okay, so I've just given them names. They have something to do with the data. It's easier to write these down than it is to write these down. So real quickly, does anybody know what the expectation is of this posterior? If you knew what the expectation of the prior is, you know how to compute the expectation of the posterior. You would substitute all your alphas for alpha tilde, and all your betas for beta tilde. So, what's the expectation of this beta right here? Let's just go back here. So the expectation of P. And I'm going to suppress the notation. I'm not putting alpha and beta in there. Just want you to get used to looking at that. For a lot of Bayesians, if they're not telling you their hyperparameterization, you ask them right away. How did you pick it? What is it? Could matter a lot. Might not have much impact on the analysis. We need to know. So they'll tell you. They're obliged to tell you. They have to tell you. Like when you talk to a lawyer, there's certain things they have to disclose to you. All Bayesians know, and at the end of this class, you'll know. So when you tell people they're the priors, you'll see up front hyperparameterization. If somebody asks you, you are obligated to tell them. What is this? Some of you studied for a qualifying exam lately. Knowing your distributions and maybe knowing the expectations could help you out a ton. So you went through and you learned all those, you wrote them down a lot. Mohammed?
Alpha over alpha plus beta.
It's alpha over alpha plus beta. The math makes people not want to speak as much. I know this because Mohammed was in one of my classes before, and he would throw out the answer every chance. The math. I think it's that, right?
Yes.
I think so. The variance. Do you know?
Alpha beta squared over alpha plus beta plus 1.
You're thinking of gamma.
But
This one's hard, so I don't expect anybody to know. Sierra, you got it?
Alpha times beta divided by alpha plus beta squared times alpha plus beta plus 1.
Yeah, that's it. Good job. So I am impressed.
Flashcards.
So, alpha times beta over alpha plus beta squared times alpha plus beta plus 1. How did you know that?
Flashcards.
Flashcards. So she made herself flashcards to be prepared for the qualifying exam a couple of years ago, and she still knows. And you probably flip through your flashcards every once in a while because you want to be a professor. So I put it on my hand earlier this morning. I also set out the web page myself. I usually have a note, so I was going to cheat. I didn't know. So some of these are a little bit more obscure. So I probably wouldn't work this out by hand. But let's just think about the expectation now down in terms of our posterior distribution. I'm going to write this down. I'll actually just write it down on another piece of paper so we can see it more clearly. So, expectation, P given X, is equal to alpha tilde over alpha tilde plus beta tilde. You might want to think about this. So let's write down what this actually is. A lot of cancellation. Those cancel. This is just sum of the xi's plus alpha over n plus alpha plus beta. Does that look familiar? Kind of looks like something. It almost looks like a mean, but not quite. There's this extra little penalty. So as n goes to infinity, we notice that this is x bar. If you put in big alpha and big beta, that is going to converge slower. Asymptotically the same, practically slower. So I never really liked the asymptotic argument. Asymptotically, they're the same. Well, what is it? What's n? Because if it's like 42, it makes a big difference. So context, it's the problem at hand. They're not all the same, even though the mechanics might look similar. But we do get an idea that we probably don't want alpha to be too big. Alpha is influencing and upweighting the number of successes. If I thought maybe a priori I was flipping a unfair point, I could encode that into the prior. So if I knew, oh, that's Scotland right there, he's always got these unfair coins. I know where he gets them from. He buys them from Amazon, where everybody gets them, and I know that they're always 0.8, 0.2 coins. So I think that I'm going to encode. That's a lot of things to think, and it might be hard to convince somebody else without them seeing things previously. So sometimes Bayesians are kind of frequentists that they're looking back and they're trying to calibrate things. I'm not sure how you would exactly convince somebody. Alpha over alpha plus beta, I could multiply by a constant all the way through on alpha and beta, and that constant could cancel in the ratio, but it certainly impacts the variance. So if I crank those numbers really high, alpha and beta, then I'm compressing what I think. So let's say alpha and beta were each 1. Expectation is centered at 0.5, 1 over 1 plus 1 in that case. That's where I'm centering it. But the variance is some number. If I ended up making those numbers 10 and 10, the expectation is still a half, but the prior is getting compressed towards the center. So, and that's what's going to happen. It happens because that's squaring. There's a lot of extra stuff in the denominator, bringing down the variance when you crank those numbers up. So, we need to think about this expression a little bit, but also the posterior is not just the expectation and it's not the variance. So I've coded this up. Let's go back and look at what this example looks like. So far the math is just algebra, pretty easy. We haven't had to integrate anything. So we will eventually, and sometimes I have shortcuts for you. Let's look at my code real quick. So I made this piece of code. I uploaded, I think, a copy very similar to this. I think I changed some of the printing options. So in the display, I went through this and I was like, I can make this update where I want it to for examples in the class. Is this online? You guys looked at it? So all the functionality is the same. I did change something in this copy though. It just has to do with the legend. When the legend appears and gets reprinted. So nothing I'm going to code up in this class is ever going to be very fancy. I like the for loops so that you can see what's happening. So I write it like C. But if you were to do this in practice, you should use the vectorized forms, especially if you're going to run it a lot. Speed things up, multi-thread it real quick. So I'll say this is intentionally slow. But I think it gives us all the ability to. It's going to take in some inputs. P, this is true P, right here. So that's what's going to be fed into it. Alpha and beta are those hyperparameters. So we'll see the impact of the prior. And then I'll say how many times I want to flip this form. So we can watch it evolve a little bit. So I just kind of pre-sorted everything. I have the beta distribution, so for like the priors right here, I've just taken a PDF and I evaluated it across the parameter values that I want to enumerate. So all I've done is I've chopped that curve up into a grid. I can't plot an actual continuum. And so I tried to pick a number of points to partition everything so it looks smooth to you. And then I connect it with a line. And we think it's a PDF. I also normalize everything too. So I re-normalize everything. But this is effectively what I'm doing. I have some controls for my axes, my plots. I want everything to fit real nice. I plot the truth in here as well. So on my graph, there's going to be a blue, kind of a thicker line, evaluation of the truth. So you can compare everything to the truth. Then everything is just running this iteratively, and I'm going to flip the coin iteratively. You could do this much faster if you just did it all at once. But I like to watch it happen. So I have some pause statements in here, and that's what's going to stop it so we can watch it. I like to watch it go slow, but at first I like to press the space bar so we can see what happened. That's how I control that. Everything is just a posterior update. So the likelihood is just that function that I had before. P raised to the number of successes and the number of failures. I've got the prior. And so I can construct a posterior. The posterior is being constructed as just this beta PDF with these updated values. And that's what we saw last time. That's what we saw on the piece of paper. I clear my figure every time. You know I do this. I'm going to keep plotting on top of the same figure. I had this really great experience one time that I was trying to debug some code, and I kept creating this plot. It would plot everything on top of each other. And I thought that meant that it just colored in the picture, the dot. It actually replotted everything right on top of each other, was storing that in memory. And so sometimes you'll notice this memory leak if you start having a graphic updated. And so you need to clear the figure out so you don't just watch your RAM go down and down and down. That was a long time ago. So, but I still remember, like, what the heck is going on? Of course, there's a profiler built in here. I'd encourage you to use it, and you can spot that stuff. So this isn't a class on MATLAB, but it's a pretty useful tool. R also has all of the same sort of functionality, and the issues are the same. So everything else is just plotting everything. So it's plotting all those values of the likelihood, the prior, the posterior as it updates. The prior doesn't update. So in Bayesian analyses, you probably shouldn't update your prior. So in a sequential analysis, there's a scheme where you use your old posterior as your prior. We'll talk about that later, what that means. The likelihood is getting reformed up. So there are sequential updating schemes, but my original prior never changes in this analysis. It's just that same thing. It's true in sequential updating as well. You might think about it slightly different. That's why we have to go through it. So this is the whole piece of code. Let's just run it. I have 0.7, 1, and 1. If you think about the beta function, p to the 1 minus 1 is 1. So same thing, p to the beta minus 1, 1 minus 1 is also 1. So that's a uniform distribution right there. There's my prior, there's the truth. So grab it out and try to do this side by side. Flip the coin, I got a 1, that's my likelihood function. You can see the posterior right on top of it. So you can even see that little differentiation right in there. So they're the same things, but give it a little bit of a jolt. Two successes, p squared. That's my likelihood function. Multiply by 1, same thing. Lots of successes this time.
Yes, that's coins.
Exactly.
That coin is a tricky one, I guess.
Yeah, right. Okay, that was a lot of successes. Let's do this. It's not impossible. So, never seen that happen before though. It's 0.7. It's unlikely to happen like that. It's even more unlikely if it ever happens. One second, I have to cough. And not sit. And cough all the time.
Just gonna sit here, press enter, so we see a 0. Where to go again? I guess it could be. I keep seeing 0. Is this a joke? No? Right, there we go. All right, we found out the opposite of a 0, which is a 1. There we go. Woo! I was scared for his code for a second. Boom. You start noticing that the posterior starts to pull towards the blue. We'll run it one more time, because why not? And let's see if we can maybe not get all ones real quick. And we will. What? Sorry. There we go. There we go. There we go. We're getting closer. Boom. got a weird code. The second time I did it, we pretty much got almost all zeros again.
Random number generation. I get an itch in the back of my throat sometimes when I cough the first time. When it shows up, I either have to cough 100 times to take a sip of water. So I'll bring my water in. Okay, let's just come back. It is a little bit weird sometimes. Let's just put 100 coin flips in there. See what happens. And I can also take out this pause right here. So it's going to pause for just a moment, so it has enough time to render the figure as well.
We might have to stop the call in the console. Control C to stop it.
What is it?
In the call, can you save and restart the code when it is running on the Mac? Because it's waiting for you in the command window to continue. So you might want to put Control C in the command window to stop it. Now you can update and save on the Mac.
Did editor at the top?
Go to the fourth tab on the top.
Yes, there it is. Boom. Let's see. This is
It's happening.
It's happening?
Yeah. Your screen's just covering the graph.
Oh, here it is. And a pause. 2 pauses. There we go. There's a second pause buried in there. So that's the posterior evolving. Changing. You can see a little bit of the discretization at the bend. You'll start to notice that posterior, while it's overlapping the truth and honing in on it, it's becoming more and more symmetric as well. And that's kind of cool. Let's do this 1,000 times. Have a look at it. So the asymmetry is wearing off in the posterior. That posterior was once a straight line. And then it was kind of really weird and had a lot of skewness to it. And now it's becoming more and more symmetric, and it has a shape that we're familiar with. What do you think that's starting to look like? It's starting to look Gaussian. So it's starting to look more and more Gaussian all the time. And that's kind of fun to think about, because if you think about some of the xi's, that's governed by a limit theorem. We usually use it some of the xi's over n. That's governed by the same limit theorem. So that's converging to the truth, but it's converging in a normally distributed way. And in the central limit theorem, our answer is stacked around. I have it so it's scaled, so you can always see down the action of the plot. So I'm reshaping the axes. But the point remains the same, is that's getting really, really high. It's getting tall. I could have changed the axis setting. I don't usually run it, so it gets so peaky. But I want you to keep watching how this gets peakier and peakier and peakier. So we're watching the limit right here. But that's starting to look more and more normally distributed. So if you worked a Bayesian, you'd do analysis probably on X bar here, and you would invoke the central limit theorem. Now, if n was like 7, X bar is not a continuous thing. So if n was 7, it's jumping around. There's a lot of discretization, and that's a bad approximation. So the central limit theorem is an approximation that gets better and better as n gets bigger. And if you've taken my inference class or an inference class, you learned about the central limit theorem. I haven't told you about the central limit theorem and the normality, but we can see that it's looking about right. That's what happens. Exponential family distributions have nice properties. So This distribution, x bar pops up, is the sufficient statistic in the likelihood for some of the xi's, and no surprise there's a connection with the central limit theorem. No surprise, this beta density has become very symmetric and have exponential tails in the limit. I'll let you do the calculus to show that. What I like about this is it's honing in and in and in. And if I flip the coin a bazillion times, all at once, this curve would start to concentrate right on that blue line. And it would become infinitely tall. So it would become a point mass function. An infinitely tall thing that has area 1 underneath it. The width is getting close to 0. So the height has to be getting close to higher than whatever number you're thinking. So bigger and bigger and bigger. That's what happens right here. So Bayesian asymptotics are pretty good here. And if we think about the expectation, that quantity is some of the xi's get bigger and bigger and bigger, alpha and beta don't matter anymore. So this is really just kind of a likelihood function that we're looking at, and the prior is wearing off. And so early on in the analysis, the prior kind of mattered for the first couple coin flips. Remember, I just plugged in alpha and beta as 1 here. I want to reanalyze the prior and think about what happens. But the posterior looks pretty good. And this was a pretty easy thing to do. And I didn't even have to know about central limit theorem to invoke this. Just did likelihood times prior. I picked a prior that was easy to update the posterior. And I thought very little about those hyperparameters. I think you can all tell that if I'm just kind of reasonable with the hyperparameters, it's not going to make any difference so long as n is moderately large. Okay, that's not theoretical, but at least in an applied setting, it kind of makes sense. Let's do this just 10 times right here, and I'm going to change my prior. Does anybody have any numbers you want me to pick? Half and half. So random. So, good choices. You all know that the half-half is usually what most people will default on. We need a better explanation of that. But if I were to pick parameters and the thing was set up like this, and I knew I wasn't being funny about, injecting information about me knowing P, so I know it's 0.7, I didn't use that in any of our rationale. So, since you know it's 0.7, you might say, I'm going to cheat a little bit, and I'm going to make alpha 7 and beta 3. And now I'm going to cheat a lot. I'm going to make alpha 70 and beta 30. So I'm encoding the truth. And I'm pinching the variance down. That's called cheating. But I could demonstrate it. But let's use half-half. It's a pretty fun example. The prior is this U-shaped thing. And I like the shape of this. It makes me happy when I see this shape. Because I know about this point 0 and this point 1 right here. That the asymptotics and the likelihood function, or the central limit theorem, or however I want to think about the analysis, we do worse over by the endpoints. In the middle, we do a really good job of estimating everything. Why is that true? There's a lot of variability in the ones and zeros, and that variability gives us the ability to distinguish things. So, if I want to be really close to the truth over here, and let's say truth Q was very close to 0, it's really hard for me to learn that if I can ever see a success, what the complement side of everything is. It messes you up. Let's do a quick experiment. How many of us are vegetarians? And I mean strict vegetarians. None of this like, I want to be a vegetarian, I'm hanging with my friends, I don't like eating a lot of meat. I don't like eating a lot of meat either. And I kind of restrict, and sometimes, but I mean strict. Never have milk. You don't, no dairy. Anybody? Okay, who's a kind of vegetarian? Lacto-ovo. Okay. Who is a carnivore? So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 Sierra, 19 me. So sample size is pretty accurate, right? Feel pretty good about that. I'm going to extrapolate the entire Virginia Tech population. There is nobody on campus that is a vegetarian. We did lacto too. I should have just started there. I wanted to get 0. So I started there. I've had classes where there's like 4 vegetarians in the class. It's like crap. So sample size is relatively small. We know there's vegetarians at Virginia Tech, especially the lacto type. They're pretty common. So if we are in California, half the class. So, but we want to put a little bit of penalty over on these sides. I want to say it could be 0, could be 1. So in our case right here, when I'm talking about the possibility of their, I think that the sample size is a little bit small. I want to penalize to say that I know it's not 0 and I know it's not 1. Probably something else. If we're doing statistics, that kind of makes sense. If I thought it was 0 and it's impossible, probably not check it out. We never see it. So hard to do stats in a case like that. So this U shape is penalizing the endpoints and stacking a little bit of mess there because small samples don't have information about those endpoints. And so I want to put a penalizer over there and put a little bit of weight. This is symmetric, and it's pretty flat in the middle. So it doesn't have much penalty in the middle, it just has penalty on the endpoints. Some of you have done this experiment before. If you've taken my inference class, you've done it. I may ask you guys to redo it. It's such a good experiment. But let's just think about the standard wall estimator. Let me go to my dot cam real quick. And I'll remind you something. This is not a very good way of doing this problem. But I think I just want to talk about the non-Bayesian of thinking about this, at least the easy thing. Change input document. So the wall interval. We haven't talked too much about intervals. We'll be getting into them. But the standard wall interval is x bar plus or minus 1.96 times the standard error. The standard error in this case, does anybody know what it is off the top of your head? You probably know what variance is. So what you normally do, you have p times 1 minus p
Push the paper
over
up.
n. And that's our variance for this problem. As n gets bigger, it starts going down. We don't know p, so we need some estimators of that. X bar, X bar. So we just write down square root of x bar, 1 minus x bar over n. So this is the clunky normal approximation confidence interval. Some people learn clunky interpretations of these intervals, but the interval is a good estimator of what p is, coverage. That's the correct way to think about it. Bayesian intervals are talking about where they think p lives. But in this interval right here, I'm going to ask a question. If I use this interval, and I wanted to look at a frequentist procedure, some of you have done this already. If I wanted to entertain a frequentist procedure, and I said true p was 1% or smaller. So the true p is over here, so I'm going to simulate from it. That interval that I wrote down is supposed to be 95% coverage. Now, I'm not too much of a stickler. I'll say if you happen to cover true p 94% of the time or 96% of the time or anything in there, that's good enough for me. The way I say that is being within 1% of the nominal rate. So you're hoping for coverage 95% of the time. If you've ever taken a Stat 101 class, that's what they taught you. So it's supposed to be in the middle of the interval. It works pretty good, about 95% coverage. So here's my question. If I wanted to be within 1% of the true nominal rate, and true P was 1% or less, where these procedures tend to break down, how big would N need to be? So the procedures get better if N gets bigger. So let me just say it again. True P is 1% or less, so it's small, 0.01 or less. And I want to have my walled interval cover about 95% of the time. Within 1%, I'll accept as a coverage. So if you cover 94% of the time, that's all right. Cover 96% of the time, I'll take that as close enough. And that's how I do think about things a lot of times. It's like close enough. So nothing's perfect. How big would N need to be? Anybody want to take a guess? 31, right? Bigger than 30. That's what I learned in my stat class. 32. It's like 9,000. So it doesn't work very good. The Bayesian with their prior is penalizing that. So they're putting a little bit of mass over there to give the analysis some traction. And so if you use a prior that kind of upweighted those endpoints, you shield against that. And that's what this prior is really showing you. We're already there. So this prior is doing exactly that for U-shape. My own prior is uniform. This works better near the endpoints, estimating things near the endpoints. Let me do another analysis where I just kind of use X bar is my estimator. So if I ended up having an alpha nadir of 0 or something like that. If I try to estimate the number of fish in the sea, I'm going to do this very poor procedure, but I'm going to do it unbiased. I'm going to go with the Dixie cup. That's just a small cup. So I don't know if they make those anymore. Do they make those? Probably not allowed to say Dixie. But it's this type of cup you can buy in the grocery store. They still sell them. That's what we call them on the West Coast. And I scooped up some water and I counted the number of fish in it. It should be like an unbiased thing. And I have this very special cup that when it scoops, it's unbiasedly scooping from the ocean. I see 0 fish, and I declare there's 0 fish in the entire ocean. I can multiply 0 by the ratio of the volumes of my cup to the ratio of volume of the ocean. Ultimately, this is just putting some traction on these endpoints so that you can estimate them. And so, looks kind of funny. If I ended up taking a different prior, let's say this is like 100 and 100, you might be thinking this is an unbiased thing right here, this prior distribution. It looks so peaky, it's off the top of the screen. The expectation is a half. But what I'm really saying with this prior is that I believe so highly that it's 1/2. And I've got just a little bit of fudge room. I think it's between 0.4 and 0.6, and I'm going to stack a lot of weight there. So that means I heavily believe that the coin is 1/2. Not just equal on both sides, but scrunched near the middle. You'll notice that the prior has some amount of impact on the posterior. So here's the likelihood function right here. It's over the blue. And the prior distribution is this black line, and it has a lot of say over what the posterior is. So if you came in with a beta prior and you said, really want this thing to be half, really insist. So my science in my career depends on it. You could cheat the analysis and put a lot of weight in the prior. But if you ever showed anybody the likelihood function, they'd say, wait a minute, your prior beliefs totally disagree with what the data is saying, i.e. what the likelihood is saying. It's governed by the data. And there's no data in the prior the way that we formed it. Most people consider that a gross violation if you do it. We'll talk about that next time. But we're going to come back, we're going to look at the normal example for this. and talk about analogs, but it'll help us also to think about prior impacts and how we want to calibrate our priors. So we might also start thinking about limiting our prior as well and start taking the limiting distribution. But in this example, I think the simulation is really informative. So go home, play around with it, see what happens, but I think it'll match your intuition as well. When I do think about the function p raised to the number of successes and 1 minus p raised to the number of failures, and then I penalize with alpha and beta, I think about that function. I can't see this shape necessarily, how flexible it is. And I think once you see the simulation, it's like, it's a lot cooler than just that formula looks on paper. So Bayesian analyses a lot of times can be rather flexible, even though this has a parametric limitation. So I have to believe in that parametric form, but it was still pretty flexible. Anyway, that's it for now, guys.